Hi everyone, welcome to our talk titled Depth Queue Conflicts Between Real and Virtual Objects Disrupt Visually Guided Reaching in Augmented Reality. So given the nature of this conference, I'm sure most people are familiar with augmented reality, but in simple terms, it's when there's the simultaneous views of the real world and virtual content that's superimposed in that world. And there have been many improvements in displays, tracking, and computational power, which have driven AR technology towards more mainstream adoption. Some common examples of this are optical see-through displays, such as the HoloLens, the Magic Leap, and the Meta Orion glasses. One of the key aspects for integration between real and virtual objects in AR is spatial localization. Many of these types of AR displays contain depth sensing cameras and head pose information from the user. For example, suppose the image on the right is a real-world environment. An AR display can spatially map the layout of the physical environment using these depth sensing cameras. This produces a mesh that conforms to the 3D geometry of the scene, and this mesh is crucial for rendering and localizing virtual object positions, especially when it's relative to the real-world surroundings. Because of these capabilities, AR technology has been developed for a variety of applications. Some common ones are image-guided surgery, education, and occupational training. But in each of these scenarios, a critical component is accurately and precisely interacting with virtual objects in combination with the 3D space of the real world. For example, some image-guided surgeries require a margin of error that is on the order of millimeters. This type of accuracy and precision for spatial localization is particularly challenging in immersive stereoscopic displays. One of the main reasons for this is the vergence accommodation conflict, which I will refer to as VAC. This occurs when the vergence and accommodative distances do not match, and it's been shown to distort perceived depth and lead to general user discomfort. Under natural viewing, for example, when looking at a monitor, the accommodative or focus distance is the same as the vergence distance. Where we converge is the same point as where we accommodate. In stereoscopic displays, however, the accommodative distance is often fixed, and the vergence distance can vary depending on where the virtual content is rendered. In this example, the user is converging at a virtual distance in blue closer than that of the accommodative distance represented by the white plane. This presents a unique viewing challenge in AR because when virtual and real objects coexist in the same space, virtual objects may be viewed under VAC, while real objects will not. And there has been some prior work done on the impact of VAC in AR, specifically what happens to the perceived relative distances between real and virtual objects. These studies used a distance matching task where the participant adjusted the position of a physical probe to match the perceived distance of a virtual target. What they found was when the focal distance was greater than that of the vergence distance, virtual targets were perceived farther than their true rendered position. As a consequence, the probe was adjusted further in order to match that perceived offset. The prior work on VAC has largely been conducted under controlled viewing conditions by isolating specific depth cues. However, natural AR use cases typically involve multiple depth cues together and interactive visual feedback. Therefore, in the current study, we introduce a real-time feedback ring placement task in AR in order to examine whether the presence of multiple depth cues can mitigate VAC-induced distortions, and if interactive visual feedback can lead to task improvement and spatial recalibration. In experiment 1, participants placed a virtual ring over a post at one of 3 distances. All virtual content was viewed using the HoloLens 2. The virtual ring was tracked to the observer's index fingertip and offset laterally using the HoloLens 2 hand tracking feature. We used a between subjects design where participants were placed into one of 2 groups, a real post group where the posts were physical objects, and a virtual post group where the posts were virtual versions of the physical posts. The HoloLens 2 has a reported focal distance of about 2 meters, So in the real post group, the ring was viewed under VAC because the vergence distance is closer, but the posts were not viewed with VAC as they were real-world objects. In the virtual post group, both the ring and post were viewed under VAC, so any distortions in perceived depth would theoretically be consistent. Each group performed the ring placement task binocularly and monocularly with an eye patch. For both groups, each trial began with a text-based prompt on which target post to place the ring on, red, green, or black. During the act of placement, the ring was rendered with a blue vertically striped texture. If at any point the ring made contact with the post, it would turn red and fall, signifying a failed attempt. Participants were given a total of 5 attempts per trial, and there were 5 trials per post. If all 5 attempts failed, the experiment would automatically proceed to the next trial. If the ring was placed more than halfway down the post without any collision, it would turn yellow, indicating a successful attempt. Now I'll show the results for experiment 1. This plot depicts a top-down view of the posts with the Z or distance position on the vertical axis plotted against the X or lateral position on the horizontal axis. The left column of plots is for the binocular condition, and the right column is the monocular condition. Blue represents the real post group, and light red is the virtual group. So these solid black rings are the average ring placements across all attempts, and it does appear quite accurate. However, when looking at individual placements shown with the light gray rings, there was more variability in the real post group compared to the virtual group under binocular viewing. And in both groups under monocular viewing, placements were highly variable with both over and underestimations. This variability is also reflected in the performance of each group. Here, the mean number of failed attempts is plotted as a function of each post distance. Under binocular viewing, the real post group had between 10 and 15 failed attempts on average. The virtual group, on the other hand, performed much better with very few failed attempts. Under monocular viewing, both groups performed poorly, with the real group trending slightly worse than the virtual group. And in this plot, we are examining potential training and recalibration over time. The number of failed attempts is plotted as a function of trial number for each group. Linear fits were made to see if the number of failed attempts decrease over trials. Solid lines are binocular condition, and the dashed lines are the monocular condition. In the real post group, under monocular viewing, the number of failed attempts showed no change over trials. However, there was a slight decrease in failed attempts under binocular viewing, but it did not eliminate the errors completely. Interestingly, in the virtual group, failed attempts slightly decreased under monocular viewing, and no change was observed under binocular viewing, but performance was so good that it was already near perfect. Overall, we found that accuracy was highest in the virtual group under binocular viewing, lower for the real post group under binocular viewing, and lowest under monocular viewing for both groups. This was reflected in the reduced performance of the real post group with more failed attempts. There was a slight improvement across trials, but errors were not completely eliminated. And this shows that distortions in perceived distance between real and virtual objects persist even when there are multiple depth cues and visual feedback is available. The ring placement results from experiment 1 showed no consistent directional errors, and this may have been due to participants trying different strategies over time and attempting to recalibrate. However, as mentioned in the introduction, previous work has shown that VAC can distort the perceived distance of virtual objects to be farther than their true position. This was reflected with a real probe being adjusted farther in order to match that offset. In our study, however, we had the opposite configuration where the probe was a virtual ring and the target was a real post. Therefore, it's possible that the ring was perceived to be further than its actual position, and theoretically, observers would adjust the position closer to compensate for this bias. We did not observe this directional trend in experiment 1, but with a controlled task with a reversed virtual probe physical target configuration, a virtual probe should yield closer adjustments. Therefore, we conducted a binocular distance matching task. Participants matched the perceived distance of a real reference post by adjusting the distance of a virtual post using a controller. Here, this plot depicts a top-down view of the real reference posts with the Z or distance position on the vertical axis and the X or lateral position on the horizontal axis. These are distance matching results with the large light-colored circles as the mean and small points as individual results. Observers adjusted the virtual posts closer than the real reference posts across all distances. This is also reflected in the mean directional error of each post. Overall, we found that virtual posts were consistently positioned closer than their corresponding references regardless of distance, and as hypothesized, this directional error is consistent with offsets from VAC-related distortions. Although the magnitude of this bias was just over 1 centimeter, it was still large enough to produce ring post collisions in experiment 1. To conclude, we observed errors in spatial alignment between real and virtual objects despite the presence of multiple depth cues. Task performance was superior when both the ring and the post were virtual, and only modest improvements in task performance over time were observed with visual feedback. This type of resilience to training highlights the importance of minimizing the mismatch between vergence and focal distances in AR, especially when precision is required. And with that, I'd like to thank my collaborators and thank you for your attention.